Welcome to Geotechnical Engineering Design. In this lesson, lesson 11, the idea is to go a little bit deeper in many concepts we have been studying in the previous videos. So the idea is to try to unify all these concepts to understand that they are actually related one to each other and in which way they are related. These topics are much more complex than the concept we have been studying before. So, and we are not going to go all the deeper we can go because there are, let's say, several mathematical demonstrations, and it's certainly necessary to have skills in mathematics at high level. But what I'm interested in this video is to share with you the concepts and the way these concepts are related in geotechnical engineering design. We're going to talk about the Mohr circle in geotechnical design specifically. We are going to introduce the concept of tensors in the stress-strain relationship in soil mechanics and in general in computational mechanics. We are going to talk again about soil strength, but relating this concept with the stress-strain relationship and the stress-strain tensors, as well as the Mohr circle. And we're going to talk about the Mohr-Coulomb failure criteria. And we're going to see at the end of the presentation that all these topics are related and they help us to understand in a very accurate way with a very relatively complex model the mechanical behavior of soils in geotechnical engineering. So let's start. So in the first place, I wanted to talk about, the difference between the geotechnical problems and structural problems. So when we're talking about geotechnical problems, we think automatically in soils because we are talking about foundations, we are talking about a dam, for example, made with soil material. So our material is going to be natural and complex because it's formed by particles that are different in nature. They can be clay, they can be sand, they can be lime, they can be gravel. So they are all natural materials subjected to environmental changes that produce at the same time different loads and change the properties of the soil itself. The interaction in the pores of the soil with water, generally with water, produce a very complex behavior in terms of the mechanical response to loads, and this is the reason why geotechnical problems are usually more complex than structural problems. But this all depends on what is the degree of complexity we are treating in every area. And a structural problem, as a difference, deal with materials that are artificial materials. So the material have, let's say, a simpler mechanical behavior because the material is more stable. And usually, the water is not playing a role in the pores of the particles because, for example, in this structural problem that is represented by a cantilever beam in this video, is a material that will be a reinforced concrete, for example, that can be pre-stress or post-stress or whatever the complexity you want to do, but the material itself is going to have certain stability with time. Of course, I'm not forgetting here problems like fatigue or creep, for example, in a structure, which are complex problems, but we have as well creep and consolidation, for example, in geotechnical engineering. And the problem again with soils is that the soil is a natural material, so we don't have control in the properties because the properties as well are affected by the environmental changes. So this is the reason why I'm saying maybe the geotechnical problems are the most complex in terms of the mechanical behavior. We're going to introduce the concept of tensor in mechanics. Is because this concept is general. It's not only for soil mechanics or for geotechnical engineering. It's for structures and it's actually for any problem in mechanics. Mechanics is the mother of all these areas we deal with in engineering. But the important concept is to realize that the problems in reality are three-dimensional. So they are 3D problems, as we want to call it. And we always need a reference to know directions in 3D. So for example, we have in here the coordinate system X, Y, and Z. And at any point of the mass soil or at any point of your structure, you will have a distribution of stresses on a point that we can represent with this scheme here. So we have a small cube. This is an infinitesimal cube, so it's a very, very small cube. And in every face of this cube, you will have axial stresses that we are going to call sigma x, sigma z, and sigma y in the three directions of the three-dimensional space. And in every face of this cube, you will have a set of a pair of shear forces in every face. So in total, you have 9 components that define what is called the state of the stresses in a point of a mass soil of an structure. This cube that have, all these stresses applied can be represented by a matrix. That a matrix is, a mathematical entity, but at the same time, this has a name which is a tensor, because it's a particular mathematical entity that is not exactly a matrix, but we can represent as a matrix. We are not here to define mathematically the stress tensor, but it's good to mention that the stress tensor is not a matrix by definition, but we can represent the stress tensor as a matrix. So for us, it's going to be a matrix at the end of the day. So this stress of the state sigma will have 3 axial stresses in the diagonal, and you have 3 and 3, in total 6 shear stresses that represent the state of the stresses at a point in the soil mass, let's say. The particularity and a property that this tensor has is that it's symmetric regarding the main diagonal in here in red. It is to say that in this, we can say that in this way, this is what we call an indicial notation. I'm not going to define the indicial notation, but I think it's intuitive, the idea that tau ij is equal to tau ji. So there is a symmetry regarding the diagonal in this tensor or in this matrix, and this is a property of the stress tensor. You know as well that there are stresses that we call the principal stresses. Principal stresses are stresses in certain directions at a point in the soil mass or in a structure where the shear stresses are equal to 0. And this is what happened in our definition of a stress tensor. And a stress tensor can be as well the stress tensor of the principal stresses, where the shear stresses are equal to 0, and you have as principal stresses sigma 1, sigma 2, and sigma 3. We usually, by convention, say that sigma 1 is greater or equal to sigma 2, which is greater and equal to sigma 3, but this is conventional, can be changed. So we need to be careful when we read literature, because not every author assume the same convention. But this is the convention we're going to follow in this explanation. Now, there is another concept which is certainly important in mechanics in general, and in structural analysis, and in the analysis of geotechnical problems, which is the problem of plane strain. A problem is called a plane strain problem when, for some reason, in the conception of our problem, we can say that one of the deformations, one of the strains in one direction, for example, the strain in the z direction is equal to 0. In the case of the dam, because the dam is very long, and this dimension is considerably bigger than the other 2 dimensions in x and y, we can imagine that under loads, and because the disposition and the direction of the loads, the deformation in this, or the strain in this direction, will be equal to 0 or very close to 0. The scales of this drawing in here is not showing exactly the idea, because this should be longer, but the concept which is important in here is that if you can say by hypothesis that the strain in one direction is equal to 0, you are in presence of a plane strain problem. And as a consequence, your stress tensor can be reduced And instead of working with the whole 3 dimensions as in here, you can reduce and you can work with the tensor, which is a let's say a two-dimensional tensor, or the tensor of second order, and you reduce the number of the variables of your stress states, and it's going to be simpler to work with the algebraic equation of this problem. In geotechnical engineering, we usually say that sigma z corresponds to sigma 2, and we work only with sigma 1 and sigma 3, which are the greatest and the smaller. Commonly in soil mechanics, the thing is that sigma 1 is different to sigma 2, but sigma 2 is equal to sigma 3. These are the principal stresses, remember. So we work usually in geotechnical engineering with sigma 1 and sigma 3. But this is again conventional, so you have to check in every book you read if this is the convention they are following or if there is any other convention in the way they work with the equations. The other problem we can face in structural mechanics, usually, not very usually in soil mechanics, I cannot imagine a problem in plane stress in soil mechanics, but you can have some examples. In this case, the axial stress in one direction is equal to 0. For example, in this problem with this cantilever beam, we realize that sigma z is going to be very close to 0 or equal to 0, and this simplifies again our stress tensor because we have these zeros in here, so we don't need to take into account these components because they are not necessary. So as you see, the difference between the plane stress and the plane strain cases are subtle, but the difference is important because conceptually it's not the same to say that the strain is equal to 0 in one direction that the stress is equal to 0 in one direction. So for now, this is enough in terms of the definition of plane stress and plane strain. You can read more about this in any book related with the structural analysis or soil mechanics at certain level and geotechnical problems. So you see that the concept of stresses we have usually when we deal with problems in 2 dimensions is simpler than the case when we are dealing with problems in 3 dimensions, because we need to introduce the concept of the stress tensor. And it's not only because it's the 3-dimensional problem. The concept of tensors and stresses in 3D is important because the software we usually use these days has all these power entities, mathematical entities programmed inside the software, and the software is able to give you the information following the definition we had made in the previous slides. So now I'm going to introduce in a little bit deeper way the concept of Mohr circles in geotechnical engineering, because we usually use the Mohr circle, but we don't demonstrate or we don't introduce the reasons why the Mohr circle works in the way it works. So again, this is related with the stress states, the state of the stresses, sorry, because the Mohr circles is a representation, a graphical representation of the state of the stresses at any point in a geotechnical problem, for example. So we are interested usually in the value of a pair of stresses, the axial stress and the shear stress, in a phase of let's say at a point in a problem. And so we are going to define certain conventions in here, but these are not important because I'm not going to explain the details of the equation. That I just want to explain the concept. If you are interested in more details about this demonstration and this mathematical equation, I can make a video for you, but you will have to ask me for these videos in the comments in YouTube. So the idea is that with this convention you have in here, you can analyze this small wedge where we represent, the traditional stresses, axial stresses and shear stresses in 2 directions, because this is a 2-dimensional problem, and we can have the definition of these axial and shear stresses in any direction, in a general direction, inclined direction on these elements. Doing that and working out the equilibrium in the x direction and in the y direction, we come up with this equation that are equation of a circle. it's not that clear that this is an equation of the circle, but if you work out and you do some change of variables, you can realize that these equations are actually the equation of a circle in a particular space, because it's not in the space of x and y, but is a circle in a space that you know, because it's a geotechnical space where you have axial stresses in the horizontal direction and shear stresses in the vertical direction. So if you study the equations in more details and you identify the radius and you identify the variables in this equation, you have the axial stresses in here, for example, and you have certain angles in here that have a meaning. You have the definition of this equation and the definition of this circle in this particular space, where the center of the circle is this value in here, which is the average of the axial stresses. The principal stresses are in the intersection of the circle and the horizontal axis sigma, and any point in this circle will represent a state of stress in a particular direction of your point in the mass soil of your geotechnical problem, for example. So you see, for example, this point in here is sigma alpha and tau alpha, which is basically this pair of axial and shear stresses in an inclined direction, a general inclined direction at your point in your geotechnical problem. The other axials, sigma x and sigma y stresses and the tau stresses, are represented, in different points of this circle. So when you have a problem, for example, and you probably remember this from your calculations in structural analysis, if you have an element in your geotechnical problem or a structural problem, and you have define the sigma x and sigma y axial stress and the tau x y shear stresses, you can locate in this space these stresses, sigma x, sigma y, and the values of the shear stresses, positive and negative. And in this way, you can define with a line that allows you to find the center of your circle, the Mohr circles, and after that, with a compass, for example, you can define the radius, and you can define these angles as well, and you can define finally the circle, the Mohr circle for your problem. Automatically, when you have the Mohr circle, you find the principal stresses for this particular problem, and in here you have defined as well the angles you are considering for this problem and the equivalence between the stresses you have as a data and the representation, the graphical representation in Mohr circle. For example, this point in here and this point in here represents the pair of axial stresses sigma x and sigma y with the positive and negative component of the shear stresses. You have to be very careful in the interpretation of this Mohr circle, because as you see, if you are talking about the tensor in 2D, in the tensor you don't have any change in the sign of the shear stress, but you have a change in the sign of the shear stress in the representation of the Mohr circle. But this is a kind of inconsistency we have to realize, and we have to know in order to not make any mistakes considering a negative sign, for example, in this matrix. So, but the important thing to know in here is that this Mohr circle represents the state of the stresses in every direction at a point in your soil mass, for example. This means that if you work out the pole, you probably remember this from previous lessons. So the pole is a point that is opposite to the original point you define with the data you have for your problem. If you connect this pole with these 2 points in here that represent the principal stresses, you get the directions where these principal stresses are located. When you get this direction, you can represent a rotated version of your elements at a point of the soil mass, and you realize the values of the principal stresses in this direction and in this direction, which are the principal stresses for this state that we started analyzing in the previous slides. So the Mohr circle is very, very powerful. It's graphical and it's simple to work with, and give you a lot of information about the state of the stresses at any point when you have a problem in geotechnical engineering or structural engineering. Now, what's happened is we want to know the axial stress and the shear stress in any direction. So let's say we want to know the axial stress and the shear stress in this inclined direction for our elements at the beginning. So we just have to realize what is the value of this angle, and we can add this angle in our Mohr circle in this way, and we have a new direction, or the direction of our inclined plane. So automatically, once we define the direction of the new plane we are interested in, we define a point in our Mohr circle, and this vertical segment in here will represent the shear stress at this plane, and the horizontal distance from here to the origin of coordinates in the horizontal axis will represent the axial stress on that plane. So with the Mohr circle, we not only find the principal stresses and the direction of the principal stresses, but we have control, or we can calculate, or we can evaluate very quickly the stresses, the axial stresses and shear stresses in any direction at any point in our geotechnical problem or structural problem. This is the power of the Mohr circle, and this is the reason why we study the Mohr circle in courses in civil engineering. The principal stresses have expressions. I'm not here to explain how to derive this expression, but if you are interested, I'm happy to produce videos explaining the derivation of these expressions. But you can find this expression in any book, and if you have as a data the axial and shear stresses at any point of your problem in geotechnical engineering or structural engineering, you can work out the values of the principal stresses using these formulas. And in these formulas, you have to recognize that this one is the location of the center of your circle, and this is the radius. So this helps a lot when you are working with this with complex problems, because you have a graphical idea of where you find the values, and you're working with a Mohr circle. This is extremely useful. I'm not going to introduce the Mohr circle in 3D, but I wanted just to mention that you can work out problems in 3D using the Mohr circles in 3D, and the Mohr circle in 3D has 3 different circles for every direction, and is much more complex than the Mohr circle in 2D, but you can do it. And in the past was very, very important because we didn't have access to sophisticated software as these days. But again, if you are interested in the Mohr circle in 3D, I can provide a presentation, or I can provide a video like this explaining details about the Mohr circles in 3D as well. Let's talk a little bit more about the stress tensor in geotechnical engineering. So we said that the stress tensor is represented by a matrix, that this matrix is symmetrical regarding the diagonal, and you can work out the stress tensor considering the principal stresses that are in this order by convention. But there are more to say about the stress tensor. If you want to study the stress tensor in every single detail, you have to study the algebraic of the stress tensor, and this is called linear algebra. In part of the analysis is called linear algebra, but it's tensor algebra the most appropriate term to describe the study of the tensors in general and the stress tensor in particular. A tensor is a mathematical entity that has properties as any mathematical entity, and one of the properties of this stress tensor that can be represented by a matrix is that the eigenvalues and eigenvectors of this entity represent the principal stresses in the case of the stress tensor and the principal directions. And this is the reason why is we work out the determinant of this expression you can see in the screen. You can derive an expression like this in here, that is the secular equation for this tensor, and this equation allows you to calculate the eigenvalues that are the principal stresses of this tensor, and the eigenvectors that are the direction of these principal stresses. But there is another set of values that are important in this equation, and these values are called the invariants of the tensor, because these values in here are independent of the direction of the reference you use to represent these tensors. Because you can change certainly the coordinate system you use to represent this tensor, and these invariants in here, they do not change because they are independent, and this is the reason why they are called invariants. They are independent of the reference you are using to represent your tensor, which is something that is extremely useful when you run complex analysis in a structural engineer or in geotechnical engineering. So let's see what these invariants look like and what are these invariants, because they are not a very complex concept to understand when you define them. So the first invariant is just the summation of the components in the diagonal of the matrix that represent the tensor. The second invariant is a little bit more complex because there are certain products and certain signs. And the third invariant is the determinant of the stress tensor, which is basically, if you have the principal stresses, just the product between the elements in the diagonal. So we demystify now the invariants because they are not that complex, but what is important in this video is to understand the concept. What is the invariant? The invariants are coefficients in this equation that represent is a particular equation that allowed us to calculate eigenvalues and eigenvectors that represent, principal stresses and principal directions for our stress tensor. We are going to see the more how useful are the invariants in the next slides. So the other thing that is important to understand in terms of tensor, that is the tensor is a representation of the stress, the state of the stresses at a point in a problem, and can be decomposed in two components. A component that we call the spherical component and a component we call the deviatoric component. And this is important because the spherical tensor have certain properties and the deviatoric tensor have other properties. So this is the way that the spherical tensor look like when you do this transformation. Yes, so you decompose the general stress tensor in two components, the spherical one and the deviatoric one we call S. And this I in here represent the identical tensor, which is a tensor that can be represented by a matrix in 3D, which is 9 components, and the diagonal is equal to 1. So all the diagonal is equal to 1. So you will have something like this, but with 1, 1, and 1. This is the I you can see here, and this is the reason why multiplying this value, sigma m, which is a scalar, by the identity tensor that you know because it's the identity matrix of 9 components, you will get this tensor as you see in the screen. The deviatoric tensor have as well invariants. We call J1, J2, and J3. You have the values in here. So the important thing is we know now the invariants are values that do not change independently of the direction or the coordinate system we use to represent this tensor. And in here, for example, as an example of a spherical tensor, we can mention the pore water pressure. You know that the pore water pressure is a stress, but this is the same in every direction, and this is the reason why we use a spherical tensor to represent the pore water pressure. And the pore water pressure can be represented as well as a scalar, the pressure itself, multiplied by the identity tensor I, and we have as a result the spherical tensor you can see in the screen in here. Now we're going to relate the concept of the tensor and the spherical tensors and the tensor in general with the definition of the effective stress we did in previous videos in geotechnical engineering. Remember that the definition of the effective stress is very simple, and it's the total stress minus the pore water pressure. But if you relate this with the definition of the stress tensor, which is a general definition for any stress tensor, and you subtract the pore water pressure, this is the expression for the effective stress in 3D using the definition of a stress tensor. You see, it's not too complicated because the pore water pressure is spherical, so affects only to the diagonal of this matrix, and this is the way that the effective stress looks like when you use the concept of tensors. This is a more compact expression of this expression you have on top, and this is the initial notation for this for this definition of the effective stress in a three-dimensional problem using the concept of a tensor, which is a concept that is used in any decent computational software these days. The spherical component of the effective stress is simply the average of the stresses minus the pore water pressure, and the deviatoric component look like this. I don't want to go in details of these equations. It's simple just to have the concepts around. But there is a consequence if you study in more details all these equations and all this expression for the tensor, that the deviatoric component of the total and effective stress tensor are the same. And what this means exactly? So the deviatoric component of the total and effective stress are the same. So this is to say that this is because the pore water pressure is spherical. So you don't change anything in terms of deviatoric components of your tensor when you apply the pore water pressure in your problem, because the pore water pressure is spherical, so affects only to the spherical component of your tensor. And this is and as a consequence, the deviatoric component of the total and effective stress are exactly the same, because you are affecting exclusively the spherical components of your tensor. As you know, in a problem you don't have only stresses, but you have strains as well, and you have two types of strains. You have the axial strains, the epsilon x, y, and z, and you have the distortions as well, which are the gammas in your problem. You know all of this because you've been doing some structural analysis, so I don't have to go in details about these strains, and I just wanted to remind you the expressions and the definitions. In the same way you have a stress, tensor stress, you have the same way you have a stress tensors, you have a strain tensors as well. And this is the definition of the strain tensors in geotechnical engineering or in structural analysis is the same. So in the diagonal you have the axial strains, and the rest are this component are the distortions in your problem, at any point at any element, square element or cubes in 3D. And again, this strain tensor have the same property as the stress tensor, so it's symmetrical regarding the diagonal. So these values in here are symmetrical with these values in here. And this tensor as well have principal direction and principal values. And of course, this tensor as well have invariants. And you have the expression of the invariance of the strain tensor in here and the deviatoric strain tensor in here, because you can decompose as well the strain tensors in a spherical component and a deviatoric component. You have more definitions in here. You probably remember this from your lessons from structural analysis. You have the volumetric strain definition in here, that is basically an invariant and is the summation of the principal component of your tensor. And you have other definitions of different, deviatoric strains. And for example, the octaedral shear deformation is something that we use in geotechnical engineering at a certain level. But in here, I'm just mentioning that there are different ways of measuring the strain. It's not only the normal strain and the deviatoric strain, but there are other components that are important as well. For example, the volumetric one and the octaedral one. As I said, you can decompose the strain tensor in spherical and deviatorics, as we did with the stress tensor. So just to have an idea and to start relating, because remember, after we are going to have the relationship between the stresses and a strain, and it's good to have the same things in both sides of our equations. So we have an spherical stress and an spherical strain. We have a deviatoric stress and we have a deviatoric strain as well. I think this is good enough as an introduction of stress and strain tensors for you at this stage. But if you are interested in more detail, let me know, because I can provide more videos in this area of geotechnical engineering and structural engineering. Let's talk now about the effective stress for saturated soils. We already defined this in previous lessons. So the effective stress, as I said before, is a very simple definition but it's a very important definition, probably the most important definition in soil mechanics and in geotechnical engineering. The effective stress is simply the total stress minus the pore water pressure. But in which direction does this stress is applied? When we define the stress in this way, we are implying that the problem is one-dimensional, because we are not talking here about directions. So the question is this a stress in 1D, 2D, or 3D? Depending on the problem we are facing, we are going to work with a more or less complex expressions. Until now, the calculation we did in our geotechnical, geotechnical engineering design problems in these videos, in this collection of videos, they were all two-dimensional problems, and we simplified the concept of effective stress in one direction. So we have been working with the definition of the effective stress in one direction only. But when you have a three-dimensional problem, you have to work with the stress tensor definition. And remember that this is what we have been studying in previous slides. And now the definition of the effective stress is a little bit more complex, because we need to introduce these indices in here that represent, in this notation, the initial notation, the concept of tensors. So the effective tensor is equal to the total tensor, the stress tensor, minus the spherical pore water pressure. You can represent in this way. But the concept of effective stress is still and remain the same. And it was, remember, it was discovered by Carl Borten-Sagi, which is the most important guy in geotechnical engineering in the 30s. And the concepts you have to remember, independently of the complexity of the tensors you use to analyze the problem, is that the deformation and soil of soil depend exclusively on the changes in the effective stress. So what matters in geotechnical problem is that you have to work with effective stress, because effective stress is what changes everything in soil problems or geotechnical problems. And that this definition or this concept is limited, because it's assuming that the solid particles are not deformable and that the water is incompressible. So this has mathematical implication that we are not going to study in this video, but we can study in videos in the future. We have defined as well the soil strain in geotechnical problems. Remember, we use one of them, and is the Mohr-Coulomb failure criteria. And the Mohr failure criteria is basically a failure criteria that includes the behavior of clays and sand, taking into account the cohesion and the angle of internal friction, the cohesion for clays and the angle of internal friction for sand. I'm not going to repeat this concept, because you have this concept in other videos, so you can watch it if you need to watch it. But let's talk a little bit more beyond what we have defined already in terms of Mohr-Coulomb failure criteria. We studied before that the Mohr-Coulomb failure criteria define lines in this space tau and sigma. Sigma is the effective stress, because the effective stress is what matters. And the cohesion is this value in here, that is the intersection of the line with the vertical axis. And the tangent of angle of the internal friction is this slope in here. But you see in this definition of this, in the graphical definition of the safe area for our problems or our state of stresses, is defined as well with minus cohesion and this other minus tangent of the angle of internal friction, which is an opposite slope to this one. This is because we are considering in our expression not only this version with this positive sign for cohesion and effective stress, but as well the negative sign are included, and we have the mirror of this line on top at the bottom as well. If we have a problem where we have defined a set of axial stresses and shear stresses, we can define the Mohr circle, and you see that the Mohr circle, because the Mohr circle is a representation of every single state of stresses in any direction at a point, we are sure that this Mohr circle is smaller than the area where we are safe, defined by our failure criteria, in this case the Mohr-Coulomb failure criteria, and we say that at this point we are safe because the stresses are not so big to touch the limits or the failure lines. If we reduce the value of the axial stress in the horizontal direction, and we are talking about reduction in here, we increase the size of the Mohr circle. So a reduction in stresses can produce a worse state of stresses in soil mechanics and in geotechnical engineering. So this is important to understand. So sooner or later, if we still, reducing the value of this axial stress in the horizontal direction, we can reach a point where we touch the failure criteria, these lines, with the Mohr circle, and this means that at this point, in this direction, at this point of the soil mass, we have reached a set of axial and shear stresses that put our soil in risk, and we reach the failure criteria we have defined as a Mohr-Coulomb failure criteria. So we are basically failing because we reach the limit, the capacity of the soil. So we have to recognize that this expression we use as a definition of Mohr-Coulomb failure criteria is the equation of a straight line. And this is the reason why we have these two lines defined, and we have the area defined, and we have a failure criteria. So the equivalence is that tau is our y, and the sigma prime, which is the effective stress, is x, and this works in the way we have defined previously. What happens now if we have a problem where we have only clay and we don't have any sand involved? We have a case where we have a clay and drain, because the clay, when it's wet and saturated, is almost impervious. So our equation of our failure criteria, our Mohr-Coulomb failure criteria, is just tau u is equal to SU. I'm using this subindex u just to represent that it's the ultimate values. So in this case, the equation of our failure criteria is a line, but it's not an inclined line, it's an horizontal line, because we only have as a variable the cohesion or the clay strength. So our space, in our space tau sigma prime, the area where we are safe is like this. So you have a set of two horizontal lines that define the limits of our failure criteria. So if we have again a case where we have a set of axial and shear stresses, we can define the Mohr circle. If the Mohr circle is inside this area, we are safe. If we, for example, reduce the axial stress in the horizontal direction, we are going to reach a point where the Mohr circle touch the lines that define our failure criteria, and we are going to reach the capacity of the soil, and we're going to break the soil basically. What happens is we have only sand. So the sand is drained because the sand is not impervious at all, has permeability, and we don't have any clay involved. So our equation is just the second terms of the original definition of the failure criteria. And in this case, the lines are passing to the center coordinates because the cohesion is equal to 0. But the concept works exactly the same. So we have, for different loads, different, Mohr circles, until we reach with the Mohr circles, and we touch with the Mohr circle the lines that define our failure criteria, and we're going to crash, and we're going to break the soil. We have studied then the stress tensor in 3D. We know that there is a property of symmetry for this tensor, and we said that there are a set of principal stresses, and this is what exactly represent the principal stresses in a problem. For example, you start with this problem where you have defined the axial stresses and shear stresses in the horizontal and the two horizontal and one vertical direction. And in order to see graphically what is the principal stress tensor graphically, let's say, this is a tensor that you find when you start rotating this cube until you reach a position where the principal stresses have the maximum value for sigma 1, the minimum value for sigma 3, and there is no any shear stress on the faces of your cube. So the principal stresses are perpendicular one to each other. This is another property of the stress tensor and of the strain tensor as well. So and this is very helpful when we run certain calculations. And on planes where we have the principal stresses, the shear stresses are equal to 0. So these two concepts are very, very important to remember because they are very, very useful when we do some analysis in geotechnical engineering and structural analysis. Finally, I wanted to end this explanation showing you the Mohr-Coulomb failure criteria in 3D in a space which is the space of the principal stresses. This is the way that the Mohr-Coulomb criteria, failure criteria in 3D looks like in the space of the principal stresses. The equation to define this volume in this space are much more complex than the straight line we use in 2D, and this is the reason why we use 2D problems many times, because it's simpler, but it's good for you to have an idea that why this Mohr-Coulomb criteria is different when we are dealing with 3D problems. It's basically because in 3D problems we have more complex equations, so we have more complex, areas. In this case, it's not an area, it's a volume that we need to define as a safe zone in our analysis of stasis at every point of our soil mass. If you see from different perspectives and different projections, the Mohr-Coulomb criteria, and I included in here the von Mises-Drucker-Prager criteria, which is another, a couple of another, criteria. They are similar but slightly different. You can see the reason why, if we project the Mohr-Coulomb failure criteria in 3D in a space which is a space in 2D, where we have the mean axial stresses in this direction that we can call as well the effective stress if you want, and this J that represent the deviatoric stresses in terms of tensors, you see that we recover the straight line we have been using in 2D problems. Remember that this is just an introduction, so I have introduced a few more complex, concepts that you just to give you an idea that how complex can be a problem in geotechnical engineering. So the problem we face in undergraduate courses are very, very simple because we try to keep the problem as simple as we can in order to have the concepts. But the important message in this presentation is that all these concepts are related and all of them are useful to do analysis in geotechnical engineering and in structural engineering in general. So the concept of the stress tensor, the concept of Mohr-Coulomb, the concept of failure criteria, the Mohr-Coulomb failure criteria, the concept of the Mohr circle, the concept of the stress tensor, and all of this, the effective stress, don't forget the effective stress, which is the most important, they are all linked and they are all useful to run very complex and very useful geotechnical analysis